guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit.
Okay, you got the flag up now, and you can see the stars and stripes on the lunar picture.
Are you getting a TV picture now, Houston?
Neil, yes, we are getting a TV picture. You're in our field of view now.
That's one small step for man, one giant leap for mankind.
The launch of the first artificial satellite in 1957 catapulted mankind into the space age. One after another, unmanned probing and manned space flights were carried out to explore our cosmic frontier, culminating in the legendary explorations of the Apollo program.
That's one small step for man.
In the Apollo program, highlighted by the first successful human landing on the moon, many on-site science experiments and return samples brought us a lot of new discoveries and views of the moon and terrestrial planets. We learned, for example, that the moon emerged about the same time as the Earth, some 4.5 billion years ago, and that the surface geology of the moon greatly differs between its near and far sides. The Apollo program came at the height of the Cold War, a geopolitical and ideological struggle between the United States and former Soviet Union that politicized space exploration, turning it into a race to the moon. Eventually, with the end of the Apollo program, many of the questions and mysteries about the moon have gone unanswered. The Selene Kaguya program began in 1999 with the intention of re-examining the questions long left over by the Apollo program. Questions such as, how was the moon born, and how did the moon evolve into what it is today? When the Selene is launched in 2007, it is hoped we can get closer to the core of the mystery of the origin and evolution of the moon. Selene is a lunar explorer mission to be organized primarily by the Japan Aerospace Exploration Agency, JAXA. It will be the most sophisticated and thorough lunar exploration mission undertaken since the Apollo program. The primary objectives of the mission will be to conduct a global observation of the moon to provide scientific data to investigate its origin and evolution. The Selene will perform precise observations and analyses of the distribution of elements and minerals on the moon's surface, its surface and subsurface structure, its gravity field and remnant magnetic field, as well as its surrounding plasma, energy particles, and lunar ionosphere. In addition to scientific objectives, the data accumulated by Selene should serve as a basis for mankind's future utilization of the moon. Selene will also look to establish fundamental technologies for future moon exploration missions, such as lunar polar orbit insertion, 3-axis attitudinal control to enable variable lunar orbital rendezvous, and various thermal controls needed to withstand the extreme variations in temperatures between lunar day and night. So what exactly will the mission of the Selene consist of and entail? Selene will consist of a main orbiter and 2 small satellites. At launch, the rectangular-shaped main orbiter will weigh approximately 3 tons and will be approximately 5 meters in height and nearly 2 meters in length and width. Its solar panel will be capable of generating approximately 3.5 kilowatts of power. The main orbiter will be sent to a circular polar orbit at an altitude of 100 kilometers. The 2 small satellites will be octagonal cylinders measuring 50 kilograms in weight, 65 centimeters in height, and 1 meter in diameter. The relay satellite will be sent into an elliptical orbit around the moon, with the Perilune and Apolloon altitudes of 100 and 2,400 kilometers respectively. The other VRAD satellite will also circle the Moon, but with the altitudes of 100 and 800 kilometers respectively. The main orbiter with the two smaller satellites will be launched together by an H-2A rocket. Once launched into space, the solar paddle and high-gain antenna of the main orbiter will be deployed, and the Explorer will orbit the Earth twice before being inserted into a transfer orbit toward the Moon. At this point, initialization checks for onboard mission instruments will take place. Once within proximity of the Moon, the main orbiter will decelerate and settle into a circular lunar orbit. The two small satellites, the relay satellite and the VRAD satellite, will then be released into two identical elliptical orbits. Once the main orbiter is circling the Moon at an altitude of 100 kilometers, it will sequentially deploy LRS antennae and lunar magnetometer mast, marking the start of a series of scientific observation missions. Selene will study the Moon in its entire surface for about 1 year. The Selene will conduct 15 observation missions. These include a global observation of elemental and mineral distribution, topography and subsurface structure, gravity and magnetic fields distribution, as well as lunar surrounding environments through highly sophisticated, high-resolution technologies. To study elemental distribution on the lunar surface, X-ray spectrometer, XRS, and gamma-ray spectrometer, GRS, will be deployed. The X-ray spectrometer will observe the energy of X-rays characteristic of elements excited by irradiation of solar X-rays to the Moon's surface, and conduct a detailed investigation of the major elemental distribution in moon rock, such as magnesium, aluminum, silicon, and iron. The gamma-ray spectrometer will create a comprehensive distribution map of lunar elements using a high-performance germanium detector to observe gamma rays. It will determine rock type from major elements such as silicon, iron, titanium, and oxygen. The presence of hydrogen can also help to determine whether or not large amounts of ice exist in the polar regions of the Moon. Because radioactive elements such as potassium, thorium, and uranium are concentrated in liquid leftover from the period of cooling and solidification of the Moon's magma, the GRS can gain clues into the thermal evolution of the Moon. Two mission instruments will be used to examine mineral distribution on the Moon: multi-band imager, MI, and spectral profiler, SP. The multi-band imager will take multicolor images of the Moon's surface through a 9-wavelength filter covering visible to near-infrared light. From the color difference, the mineral composition of the lunar surface and their distribution can be clarified. The spectral profiler measures the continuous spectroscopy of visible to near-infrared light to obtain the variety and abundance of minerals on the Moon's surface. The combination of these results with those of the multiband imager will enable a precise mapping of lunar mineral composition and distribution. Three instruments will be deployed to study the Moon's surface and subsurface structure. They are Terrain Camera, TC, Lunar Radar Sounder, LRS, and Laser Altimeter, LALT. Photographs of the lunar surface will be taken from the Terrain Camera, a pair of cameras on the main orbiter pointed at oblique fore and aft angles. The cameras have a spatial resolution of 10 meters. The disparity between the two images taken of identical locations will enable the digital terrain model of the entire Moon surface. For the Lunar Radar Sounder, 4 15-meter-long antennae are extended from the main orbiter in orbit around the Moon. For so-called sounder observation, 2 antennae will send 5 megahertz pulses, which will be bounced off the Moon. Analysis of the returning radio signal should provide a picture of the Moon's subterranean structure up to a depth of 5 kilometers. For natural radio wave observation, 4 antennae will be set to receive various signals. Low levels of noise at the far side of the Moon makes observation of natural radio waves from the Sun or other planets a highly effective form of measurement. The laser altimeter will send out laser beams toward the lunar surface. Measuring the time it takes for a beam to be reflected back will enable an accurate determination of distances. Conducting these measurements on the entire Moon surface will allow the construction of a lunar topography model with never-before-achieved levels of precision and detail. Five different experiments will be conducted to assess the environment on and around the Moon. Lunar Magnetometer, LMAG, Charged Particle Spectrometer, CPS, Plasma Energy Angle and Composition Experiment, PACE, Radio Science, RS, and Upper Atmosphere and Plasma Imager, UPI. Unlike the Earth, the Moon's magnetic field is extremely weak. Therefore, the sensor of the lunar magnetometer must be placed on the tip of a 12-meter-long mast so as not to be influenced by the magnetic field produced by the main orbiter itself, enabling precise investigation of magnetic field distribution. The charged particle spectrometer will measure alpha rays created from radon and polonium decay on the lunar surface and work to determine radon and polonium distribution and emission sources. The CPS also observes electron, proton, and baryon particles emanating from the Sun and other regions of the galaxy to determine the Moon's radiological environment. This data should eventually be of great use for future lunar exploration and development activities. Plasma around the Moon is generated by the Sun, the Earth's magnetosphere, and the lunar surface. The Plasma Energy Angle and Composition Experiment has been designed to analyze and study the behavior of plasma energy around the Moon, as well as from the Moon and Earth's respective magnetospheres. The lunar missions conducted by the former Soviet Union are believed to have revealed the presence of a lunar ionosphere. This ionosphere has been said to either result from the breakup of electrons and ions from ultraviolet rays in the Moon's thin atmosphere, or from the electron layer on the lunar surface. When radio waves pass through it, distortions are produced. With the radio science, the Moon's ionosphere can be studied by measuring the existence of distortions in radio waves that reach Earth from the VRAD satellite. The Upper Atmosphere and Plasma Imager utilizes two telescopes highly sensitive to visible and extreme ultraviolet light to measure the terrestrial plasmasphere and the global distribution of the Earth's aurora and airglow from a lunar orbit. Two-axis gimbals on the main orbiter will enable directional control of the telescopes and automatic Earth tracking. Lunar gravity fields are to be studied using the two small satellites, the relay satellite, RSAT, and the radio source, VRAD satellite. Lunar gravitational pull varies from location to location, depending upon the different densities of subsurface materials. Therefore, radio tracking of the accelerating or decelerating main orbiter can reveal how the Moon's gravity is distributed. When the main orbiter is on the far side of the Moon, the relay satellite will relay radio waves from a ground-based station and the main orbiter, thereby conducting the world's first direct measurement of gravity fields on the far side of the Moon not visible from Earth. Radio signals sent from both the relay satellite and the VRAD satellite will be received at multiple locations on Earth. Through a method that simultaneously receives radio signals from stars and two small satellites, those satellite orbits can be accurately determined, and global observation of lunar gravity fields can be conducted at unprecedented levels of precision. The high-definition television HDTV system will be deployed on the mission, equipped with a telescope and a wide-angle camera. As the satellites move in the Moon's orbit, high-definition images of the Earthrise off of the Moon's horizon will be captured for education and public outreach. The 15 observation missions of Selene should provide the world with an immense corpus of valuable information and data for more accurately understanding the origin and evolution of the Moon. It should go a long way in helping us understand how the Moon was formed, what it's made of, what it is actually like across its surface, and interior structure. The Moon is the nearest celestial body to the Earth. Much more than a perennial captivating subject of scientific study, the Moon also stands to serve as the first stepping stone of mankind's expanded activities beyond the circum-Earth orbit. Ever since the President of the United States announced the new space exploration policy in January 2004, NASA has been hard at work designing a new manned moon exploration effort to take place around 2018. Mankind's involvement with the Moon in the 21st century is certain to take on completely different objectives than the Apollo program, as future programs aim to make use of the Moon's resources. At JAXA, we too are continuously examining new possibilities for manned moon missions and aspiring to discover new ways to benefit from what the Moon can teach us. With that in mind, the Mineralogical and engineering lunar explorer Selene stands ready to open the doors to a new age of lunar exploration. And the knowledge it brings back is certain to play a profound role in the shaping of mankind's future.
I guess you're about the only person around that doesn't have TV coverage of the scene.
That's all right, I don't mind a bit.
They've got the flag up now, and you can see the stars and stripes on the lunar
Flag
picture.
up now, you can see the stars.
Are you getting a TV picture now, Houston? Neil, yes, we are getting a TV picture. You're in our field of view now.